Awesome. We've talked about how powerful MLPs are, how they can approximate any function, and how they're being used in the real world. But now it's time for some real talk, because while MLPs are great, they aren't easy to train. In fact, there are some major challenges that can turn even the best designed network into an absolute disaster. First up, the vanishing gradient problem. This happens when a network is too deep, and by the time the error signal reaches the early layers during backpropagation, it becomes so small that the first few layers barely learn anything. It's like trying to send a message through a long game of telephone. By the time it reaches the first person, it's completely garbled and useless. This is why deep networks often need special tricks like ReLU activation functions, batch normalization, or residual connections to keep the gradients from disappearing. Next, we have computational complexity. Let's be real, MLPs are resource hogs. The deeper the network, the more calculations it needs, which means more processing power, more memory, and longer training times. Training a large MLP on a standard laptop? Forget about it. That's why deep learning relies so much on GPUs and TPUs, which can handle the massive number of matrix multiplications required for training. Another challenge, the need for large data sets. MLPs are data hungry. They need a lot of labeled examples to learn meaningful patterns. Unlike traditional machine learning models, which can sometimes get away with small data sets, MLPs require thousands, if not millions, of examples to perform well. And if the dataset isn't large enough, you risk overfitting, where the model memorizes the training data instead of actually learning patterns. Speaking of overfitting, that brings us to the next problem, generalization. Just because an MLP performs well on training data doesn't mean it will do well on new data. If the model learns too many details from the training set, it won't be flexible enough to handle unseen examples. That's why we use regularization techniques like dropout, L2 regularization, and early stopping to keep the model from becoming too specialized. And finally, hyperparameter tuning. There's no magic formula for picking the right learning rate, batch size, number of layers, or neurons per layer. It's a trial and error process, often requiring techniques like grid search, random search, or Bayesian optimization to find the best settings. Get the hyperparameters wrong, and your model might learn too slowly, overfit, or fail to learn at all. So, what's the takeaway? Training an MLP is a balancing act. If it's too shallow, it won't learn complex patterns. If it's too deep, gradients vanish, computation costs skyrocket, and overfitting becomes a real threat. And without enough data, the whole thing falls apart. But don't worry, MLPs aren't the only game in town. In fact, for some tasks, other types of neural networks perform way better. For example, if we're dealing with images, wouldn't it make more sense to use a network designed specifically for visual data? Well, that's exactly why convolutional neural networks, CNNs, exist. And trust me, if you think MLPs are impressive, CNNs will blow your mind. Let's dive into that next. Yeah, we've spent a lot of time talking about MLPs and how they can approximate any function, which sounds amazing, right? But here's the thing. MLPs aren't always the best choice for every problem. And nowhere is this more obvious than when dealing with images. Imagine you're designing an AI to recognize handwritten digits. If you used an MLP, you'd have to flatten the entire image into a single row of numbers before feeding it into the network. This means the model loses all spatial relationships. It treats pixels at the top left the same as pixels at the bottom right. That's like trying to recognize someone's face by looking at a random list of their facial features instead of an actual picture. This is where convolutional neural networks, or CNNs, come in, and trust me, they are game changers for computer vision. Unlike MLPs, CNNs are designed to process images the way humans do. Instead of treating each pixel separately, they use special filters to detect edges, textures, shapes, and patterns, just like your brain does when you recognize a face. An MLP is like an overly literal person who tries to memorize everything. Show them an image of a cat and they'll remember every pixel exactly. But the moment you change anything, the angle, the lighting, the size, they get completely confused. CNNs, on the other hand, focus on key features. They look for whiskers, ears, fur texture, and they still recognize the cat even if the image looks a little different. CNNs work by scanning an image with small filters, learning to detect patterns that get more and more complex at each layer. Early layers detect simple edges and corners, middle layers recognize textures and shapes, and deeper layers put everything together to identify entire objects. This step-by-step approach makes CNNs incredibly effective at understanding visual data, far beyond what an MLP could do. And here's the best part. CNNs require way fewer parameters than MLPs because instead of trying to memorize every pixel, they share their filters across the entire image. This makes them much more efficient, meaning they can train faster and perform better even on large-scale image recognition tasks. So what's the takeaway? If you're working with data that comes in tables or spreadsheets, an MLP might be fine. But the moment your data has a spatial structure, like images, videos, or even some types of sensor data, CNNs are in a completely different league. But wait, what if the data isn't spatial but sequential? What if we're dealing with speech, time series, or natural language? That's where another type of neural network comes in, recurrent neural networks, or RNNs. And trust me, if you thought CNNs were cool, RNNs will blow your mind. Let's dive into that next. Great. By now, we know that MLPs are powerful. They can recognize patterns, approximate complex functions, and power everything from image recognition to recommendation systems. But there's one thing they struggle with: time. Think about how humans process information. If I tell you a sentence word by word, you don't just treat each word independently. You remember what was said before, connect it to what's being said now, and predict what might come next. This is where MLPs fall apart. They process everything as a fixed input, meaning they have no memory of what came before. They look at words in isolation, treating every input like it's brand new. And that's a problem if we're dealing with sequences like speech, text, or time series data. This is where recurrent neural networks, or RNNs, come in. Unlike MLPs, RNNs have a built-in memory system. They aren't just looking at the current input, they also remember previous inputs, allowing them to learn relationships over time. Instead of just analyzing one word or frame at a time, RNNs process sequences by passing information from one step to the next, updating their understanding as they go. Imagine reading a book. If you only focused on one word at a time without remembering the previous ones, the story wouldn't make any sense. RNNs solve this by maintaining a hidden state that carries information from past inputs. This makes them ideal for tasks like speech recognition, language modeling, stock market prediction, and anything else where context matters. But here's the catch. Standard RNNs struggle with long-term dependencies. As the sequence gets longer, the network starts to forget earlier information, leading to a problem known as the vanishing gradient issue. If you've ever tried to remember a phone number for too long and eventually lost track, that's exactly what happens to an RNN trying to process long sequences. To fix this, researchers developed more advanced versions of RNNs, like LSTMs and GRUs. These architectures have special gating mechanisms that decide what to remember and what to forget, making them much better at handling long-term dependencies. That's why they power things like machine translation, chatbots, and predictive text, applications that need to understand full conversations rather than just isolated words. So where does this leave MLPs? If your data is static, structured, or doesn't have a meaningful sequence, an MLP might be enough. But if your data has a time component, if past inputs influence future outputs, an RNN is usually the better choice. And now that we've covered MLPs, CNNs, and RNNs, the next big question is, what's next? AI is evolving fast, and new architectures are pushing the boundaries of what's possible. Let's take a look at where MLPs are headed in the future and how new innovations are making them even more powerful. We've covered how MLPs work, their strengths, their weaknesses, and how they compare to CNNs and RNNs, but here's the real question. Where are they headed next? Because AI isn't standing still, and MLPs are evolving in some seriously exciting ways. One of the biggest trends is dynamic layer configurations. Instead of building a fixed network and hoping for the best, researchers are developing architectures that adapt based on the complexity of the problem. Think of it like a self-adjusting camera lens. It changes focus depending on what's in front of it. This allows neural networks to be more efficient, using only the resources they need instead of overloading on unnecessary complexity. Another major innovation is transfer learning for MLPs. This technique has already revolutionized deep learning in CNNs and NLP models, allowing networks to be trained on massive data sets and then fine-tuned for smaller specific tasks. Instead of starting from scratch, MLPs can now leverage pre-trained models to learn faster and with less data, making AI more accessible to industries that don't have millions of examples to train on. Then there's the rise of attention mechanisms. Originally designed for sequence models like transformers, attention layers are now being incorporated into MLPs to improve feature selection. Instead of treating all inputs equally, attention allows the network to focus on the most important parts of the data, filtering out noise and improving accuracy. It's like highlighting key sentences in a book instead of reading every word with the same level of focus. Another exciting direction is multimodal learning, where MLPs are being integrated with other architectures to process multiple types of data at once. Imagine a system that can take text, images, and audio simultaneously, learning how they connect. This is already being used in AI assistants where speech recognition, language understanding, and image analysis all work together in a single system. And let's not forget real-time processing. With advances in hardware, MLPs are becoming fast enough to power real-time applications like autonomous vehicles, real-time fraud detection, and instant language translation. These networks are being optimized to run efficiently on mobile devices and edge computing systems, reducing the need for massive cloud servers. But perhaps the most important shift is in regularization and optimization techniques. New methods like dropout, batch normalization, and weight pruning are making MLPs more resilient, efficient, and scalable. These improvements are allowing deeper networks to train faster and better than ever before, reducing the traditional barriers of computational cost and data requirements. So, what's the big picture? MLPs are not just staying relevant, they're evolving. With smarter architectures, transfer learning, attention mechanisms, and real-time capabilities, they're becoming more powerful and flexible than ever. They may have started as simple function approximators, but they are now stepping into roles that were once thought to be exclusive to more complex architectures like CNNs and transformers. And now, with all this in mind, it's time to wrap things up. Let's take one final look at what we've learned and why MLPs continue to be a foundational tool in the AI revolution. We've covered a lot, from understanding how MLPs work to exploring their real-world